Hi everybody, my name is Tyler Foster. In this video we'll be covering the basics of lung compliance. Depending on the response that I get for this video, I might make a more complex video regarding lung compliance. However, this should be the very basic outline about lung compliance. So let's talk about lung physiology for a little bit. To do this, we're going to think about compliance theoretically, and then later on we'll get into the equation, some pressure volume curves, and some scenarios where the lung compliance changes. So to begin, we're going to take three objects that we're going to find off the street. We're going to find a plastic bag. So let's see if I can butcher a drawing here. Here's our plastic bag with the little handles. Then here's the little loop. So here's our plastic bag, one that you'd find at the grocery store. We've also got another object I'd like to think about, and that's going to be a water balloon. So we've got our water balloon here. And this is going to be one that you're going to throw at your baby brother or something. And then finally, we've got a water bottle. Okay, so we've got three items here. Let's see if I can butcher a drawing really quick. Here's a terrible example of the water bottle. Maybe it's got a label on it with a rounded bottom for some reason. So we've got three items. Now, why am I talking about these three items when I'm talking about lung compliance? Well, let's imagine for a second if you close off the end of the bag and try and blow into a flat plastic bag and try and blow it up kind of like a balloon. It's not going to take much work. Then we bump up to our next item, which is going to be the water balloon. And when we try and blow up our water balloon, we're going to encounter a little bit more resistance. It's going to be taking a little bit more pressure to increase the volume of this water balloon. It's going to take a little more work to blow it up. And then finally, we're going to blow into the end of our water bottle, try and blow it up. It is not going to happen. It is going to be very rigid. We're not going to get anywhere. No matter how much we blow into this water bottle, it'll just not blow up. So those are our three examples. Now, how does this fit into compliance? Well, if I told you that you can think of compliance kind of like stretchability. How easily an item is able to stretch or blow up given certain conditions. So in our example about our plastic bag, it didn't take much effort, didn't take much pressure to blow up that bag to a nice big volume. So we are going to say that this item is very highly compliant. It's going to be very stretchable given a certain amount of pressure. Now, if we use the same amount of pressure to blow up that water balloon, it's going to be a lot harder. So it didn't take much pressure over here. And here, if we use the same amount of pressure that we did to blow up the plastic bag, we might get a little bit response in our change in volume. We might get a little bit bigger of a balloon, but it's just not going to happen as much. So this is going to be kind of like a medium level of stretchability. And then when we get to our water bottle, if we use the exact same amount of pressure that we did to try and blow up our plastic bag, but then we apply that to our water bottle setting, we're going to say that it is not very stretchable. It has a very low compliance. So given that same amount of pressure, we are not going to get very much volume at all. Now, I said that we're going to talk about our formula later on about compliance. So this is just kind of a theoretical example about what compliance actually is. You can kind of think of it as the stretchability of an object. So let's clear that out. We're going to bring in our lungs. So now we're actually getting a little bit more involved here. So instead of focusing on the left and the right lobes of the lung, I want to focus more on the terminal airway. So that's going to be the alveolus. Let's see here. The alveolus. So it's going to be millions of these tiny little airways in each lobes of the lung here. So let's focus in on one alveoli, for example. In this alveolus, air is going to come in through our trachea, down in the bronchioles. It's going to enter in the alveolus. It's going to cross the alveolar membrane. It's going to cross the interstitium and then end its way in the bloodstream. So we've got a little nice capillary network surrounding each alveolus to pick up the oxygen that comes in. So our route is going to be through the trachea, down into the bronchiole. It's going to make its way down through the terminal bronchioles and then into the alveolus. And once it's in the alveoli, it's going to cross the membrane into the bloodstream. Why am I talking about all this? Well, it's a little more complex than I actually made it out to be. So we're going to throw in a small little layer of water on the inside of each alveolus here. So inside each alveoli, we're going to have some water tension. So even though this is a 2D picture, try and imagine it in a 3D setting. So we're going to have this big layer of water surrounding each alveoli wall. Why is this important? Well, let's think about a swimming pool. When you're in a swimming pool and there's a little diving board on the side here. So this is going to be our diving board. And you've got a person over here that's getting ready to dive. They're running towards the end. They're going to jump and they're going to belly flop. So our person is now belly flopped onto the water. Water has surface tension. A belly flop wouldn't hurt if water didn't have surface tension. And that surface tension is created by hydrogen bonds. So we're going to have a polar end, we're going to have a non-polar end, and we're going to get bonding. So when you actually hit the water on a belly flop, it's kind of like hitting cement. Eventually, yeah, it'll give, but it has surface tension. Let's bring this back to our example where when we have introducing a layer of water in our alveolus, we're going to have surface tension. And what that surface tension is going to want to do, it's going to want to try and collapse our alveoli. So it's going to want to bring our alveoli more collapse into a more atelectatic state. So it's going to create atelectasis, or a collapsed alveoli. Now, we have a great actually defense in our body on how to prevent this atelectasis, and it's going to be called surfactant. Surfactant is going to be produced by type 2 epithelial cells, or type 2 cells within the alveolus. So type 1 cells are going to be the ones that actually create this nice little alveolar wall. Type 2 cells do other things, however, one of the effects is going to be creating surfactant. Now, what is surfactant? It's going to be a phospholipid molecule. It's also known as DPPC, which stands for a more complex name, which right now it's not that important. But surfactant is going to be secreted, and it's going to be mixed in kind of to this water layer, and it's going to actually decrease the water tension. So water tension without any surfactant in the alveolus is going to pull the lung shut. However, if we add some surfactant to the mix, yeah, maybe we get some collapse, but it's just not going to be as strong. So these arrows are going to be reduced. We're not going to have as much tension pulling our alveoli shut. So how does this kind of play into the factor of lung compliance? I know I've kind of skirted around the fact. What this is going to do is it's going to decrease the collapsing pressure on the alveolus. So what we can do is we can move on and now introduce a formula here. So let's clear everything off. If I told you that compliance is equal to change in volume over change in pressure, how does that relate to anything that we just covered? Well, let's bring in the example of the lung. So in a normal state, our lung has a little bit of air in it. We have our alveoli here, and it's going to want to collapse, but at the end of the day, it's going to collapse but still have a little bit of space here in the middle. It's going to have some air left over. Now, let's get rid of that. So we have our change in volume over change in pressure. Our change in volume is going to be at the time of 0. So let's just say we exhale a normal breath. We're not trying to exhale all the air in our lungs. We're just taking a nice normal breath. And at the end of exhalation, known as the end of your tidal volume exhalation, we are going to have a little bit of air in the lungs. So let's say we have about 150 milliliters or cc's of oxygen or air in the lungs at the end of expiration. Now what we're going to do is we're going to take a nice normal breath. We're not going to try and take a nice deep breath. We're just going to take a nice normal breath. And at the end of our normal inhalation, let's say we have 350 milliliters or cc's of air in our lungs. So we have a change in volume. We started out with a little bit of air in our lungs, and we ended with some more air in the lungs. So what is this? It's going to be a change of 200 cc's. So 350 minus 150 is going to be 200 cc's or milliliters of air in the lungs. Now, we're also going to bring into the picture pressure. So the lungs are going to be a negative system. What that means is we're going to take a negative intrathoracic pressure to expand the lungs. So we have two scenarios that we can do. We've got our chest wall here. We've got some lungs that are going to be in here. Let me draw it out. Pretty bad drawer. So I got to focus. So we've got our lungs in our chest wall. What we do is we have muscles and the diaphragm. So let's introduce our muscle called the diaphragm at the base of our lungs. We've got muscles within our chest wall and our diaphragm which act to pull. So our diaphragm, when it contracts, is going to pull this way. And this is going to be a closed system. Everything is nice and closed. Our chest wall, our inspiratory muscles are going to bring our chest wall like this. And what we're doing is we're effectively creating a vacuum. So what we're doing is we're creating a negative pressure between the chest wall and the lung wall. So pleural pressure, so we have our intrapleural pressure, and what we're doing is we're creating a negative pressure, like a vacuum. So at the very end of exhalation, so in our example where we have 150 cc's, we take a nice deep breath in and out. We're not trying to exhale all the air from our lungs, but we're just getting rid of everything that we don't need right now. That's going to be our lungs collapsing. So our diaphragm is going to move up, our chest wall will move in. However, we'll still have a little bit negative of a pressure. So let's say we have -5 centimeters of water pressure just at the end of a normal exhalation. Now, what we're going to do is we're going to take a breath in, not a deep breath in, just a normal breath in to get to our 350 cc volume. What that is going to do is it's going to create more vacuum. So let's say at the end of a normal breath, we have 10 centimeters of water, -10 centimeters of water, because remember, we're in a vacuum. So we have a change in pressure. Now we go from -5 to -10 centimeters of water. What that is that's going to be a change in 5 centimeters of water. So what we're going to do is we're going to be creating our lung compliance. So these are just kind of an example here of what we're kind of looking at. So let me just pull out my calculator because I haven't actually calculated this. And math is definitely not my strong point. So 200 divided by 5, if I'm right, is going to be 40. Well, it's going to be, we have to look at our units. It's going to be 40 cc's over centimeters H2O. So, or 40 cc's times centimeters H2O to the -1. So this is going to be kind of our calculated compliance in this scenario. What does this matter? I mean, why am I even talking about all the stuff that I have up to this point? Well, let's kind of get this cleared off and move to something else. We've got scenarios in the body where we're going to have an increased compliance, and we're going to have scenarios where we have a decreased compliance. Okay, so scenarios that we have an increased compliance are going to be examples like COPD or emphysema. Also, normal aging. So our age plays into account of compliance of the lungs. So as we age, our lungs compliance is going to increase. Now remember, looking back to our very first example, let's bring that back. We have compliance, which is thought as stretchability. So as we age, our lungs go from more of like a normal water balloon to more of like a plastic bag. So also, there's a disease that's normally associated with smoking, but also a few other diseases where emphysema plays into effect. It's where we have these nice little alveoli. We have nice alveoli kind of sitting here. Emphysema is going to be where those alveoli are going to be hugely distended. We're going to lose some of the normal structural support that these alveoli have, thus leading to these nice, huge, distended alveoli where they just, so much air can get trapped in these alveoli. We also have scenarios where we have decreased lung compliance. So for example, we'll have tension pneumo, where we have air, tension pneumo, where we have air that's restricting our lungs' ability to open, thus leading to a decrease in compliance. Also pulmonary fibrosis, for example. Any scenario where you have increased abdominal pressure, so like abdominal compartment syndrome. Any scenario where you increase the abdominal pressure, or you lose some of the ability of the alveoli to kind of expand, or you have something like air or water that's preventing your lungs from expanding, any of those are going to decrease your lungs' compliance. Some of them are reversible, some of them are not. So pulmonary fibrosis can be thought of as a non-reversible cause, while increased abdominal pressure, if you relieve the abdominal pressure, your lungs will resume back to normal baseline compliance. Now, let's look at another example. I'm going to tell you that we have a curve or a graph, and what that graph is it's going to be pressure. So it's going to be our centimeters water, because that's going to be how we're going to measure our lung pressure on our x-axis, and our y-axis is going to be volume. So let's say liters here. We're going to have a 0 pressure in the lungs. We're going to have a -5. Let's throw our -10. Let's do a -15 just for giggles. We're going to use our example that we did earlier, where we calculated the lung compliance. Because remember, compliance is going to be change in volume divided by change in pressure. Now we have a graph here that has volume and pressure, so we can see our compliance and how compliance plays into the picture here. Let me change colors and let's begin. We're going to have an inspiration at time 0. Remember I said earlier that the lungs at normal end exhalation, at normal end tidal volume exhalation, we're going to have a little bit of volume in our lungs. So we're not going to start actually at the 0 volume. We'll start somewhere up where we have a little bit of volume in our lungs. So that's why I'm starting up here. We have 0 pressure. Now, at 0 pressure, what we're going to do is we're going to take a nice deep breath in. Okay, so we take our nice deep breath in. I'll show you the curve, and then I'll explain the curve in just a little bit. Now, this is kind of a funky looking shape. Initially, when we take our breath, we're going to change pressure. So we're going to be changing our pressure, but we're not going to get very much volume change. Notice how we're not making much change on our y-axis, even though we're making some progress on our x-axis here. So we're changing pressure. Our lungs are going to be expanding. Our diaphragm moves down to create our negative pressure, and we would expect that there's some volume change. However, that's actually not the case, because remember we have our water tension that's on our lungs, on our alveolus, that is wanting to collapse those lungs and drive pressure in like that. So at our initial breath, as we start off taking our breath, we're trying to fight this water pressure that's pulling the alveolus in. So we're trying to open up these atelectatic alveoluses. So we're not getting much change in volume because we're trying to fight this water pressure. However, once we've kind of broken that water pressure, remember our diving board example, so yeah, we're starting to pull things from earlier in. So once we've broken that water tension, the belly flop doesn't hurt as much because the surface tension has been broken. So we're going to start getting more volume change. Our alveolus is going to slowly start to expand as we take more and more negative pressure. As our diaphragm moves further down and our chest wall moves further out, our alveolus slowly grows, and it grows until we hit our end of inspiration, at which point we start to exhale. So this bottom, let's see if I can get, this bottom part here is going to be inhalation. This is going to be the inhalation part of our loop. Now, using deductive reasoning, we have exhalation. So our exhalation loop is going to be the top layer. So okay, so that was just me kind of putting it into perspective. We have our change in pressure. Remember I said it's a negative pressure system, so the diaphragm's moving down, creating our vacuum. At the very end, we have this point, in which case we start to switch over to our exhalation. Now, why is our exhalation loop different than our inhalation loop? Here we kind of have a slow rise, then we get to more dramatic change in volume, and then we start to level off a little bit to our point, in which case we switch over to exhalation, which normally just kind of does a little drop. Now we have two things that we need to talk about. We need to talk about the difference between our inhalation and our exhalation loop. Why do we have space between the two? Why aren't they just a nice complete picture? Well, that is because we have this thing called hysteresis. And this is going to be the difference, so we can actually turn this into kind of an equation or definition. It's going to be the difference between our inhalation and exhalation loop. So that's going to be the definition of our hysteresis. So why do we have this? It's due to the energy required that we need to break the tension and open our alveoli versus our collapsing pressure. Once our alveolus is nice and big in this example, so following this line, we're going to have water that's going to want to exert a pressure in. So we're not having to fight the water to collapse it. So we're going to get a difference here. While during inhalation we had to fight our surface tension, during exhalation our surface tension actually works for us. So it's going to help collapse the alveolus just a little bit. Also, we're going to have our lungs, our diaphragm is going to move up into the thoracic cavity, our chest wall is going to move more inward, so we're going to have less resistance that we have to fight. So that's going to be our main thing for hysteresis. We're going to have a difference between our inspiratory loop and our expiratory loop, and that's going to be due to the different forces involved in the alveolus. So this is going to be our normal situation. Let's say we have a normal lung. What if I draw in another loop? We're going to have, still going to be slow, get a nice big reach. We have our hysteresis, and they both end at the same point, no matter where you begin. So in this situation, pretend that this point right here is the exact same point as there. We're not increasing our resting volume. However, I'm showing you that we have an increase on our volume loop. If you see an increase, so kind of for example like this, from our starting point, that means you have an increase in compliance. So this is going to be our pressure volume curve. Pressure volume curve. If you see the waveform move up at the same starting value, you know that you're going to have increased compliance. And if you see the loop go down, so if I'm drawing it out and you see kind of this, you have a decrease in compliance. I'm going to leave it at that for this basic video. Really, this pressure loop curve, I've kind of broken it down into simple, tried to make it as simple as I can. If people want more of a expanded definition, I can be happy to give you that as well. However, this is going to be our basics for our pressure volume curve. We're going to measure our inspiratory loop. We're going to measure our expiratory loop. There's a difference between the two, and that difference is due to our surface tension in the alveolus. Lastly, I want to take a look. I said that this is going to be breaking our surface tension. This part right here. This part right here is going to be our nice breath due to our alveolus that's expanding. and then we start to slow down as we near the top. It's not just a nice linear curve, we start to slow down and plateau. That's because at about this size of the alveolus, during a normal nice breath, we're going to meet some resistance. Alveolus compliance is going to decrease with small lung volumes. It's going to be increased with medium lung volumes, and our compliance is going to be decreased with upper volume limit lung volumes. And that's because we're going to have elastin and fibrin elastic particles in our alveolus wall, which are going to prevent it being over distended. It's kind of like a water balloon. You're going to blow it up, and as you get a nice big water balloon, you're going to start meeting a little bit of resistance. Not a great example, because as you keep blowing, the water balloon will eventually explode, and if you blow it up too hard, your lungs really won't explode, kind of given normal volumes. You can get barotrauma and volume trauma, but that's out of the scope of this video. But in terms of compliance, as the alveolus gets really big, the compliance is actually going to decrease. So when it's small, we're going to have a very low compliance. Somewhere in this middle area, we're going to have a medium or an increased compliance. And then as we get really nice and big, we're going to have, again, a decreased compliance. So really the lung is a very dynamic structure. It all is going to be based on this formula. Compliance is equal to a change in volume over a change in pressure. Let me just go back here. We touched upon the 3 different scenarios hypothetically. So if our alveolus was a plastic bag, it would have a very high compliance. If our alveolus is a water bottle, which is kind of in the middle range, that's what our alveolus can be thought of. And then a water bottle is going to have a very low compliance. We talked about the different scenarios where you're going to see these different compliance changes. So COPD, our lung is going to be like a plastic bag. We're going to have these really large distended alveolus because you lose some of the structural support in the alveolus. Scenarios with low compliance is going to be like pulmonary fibrosis, where you're trying to breathe, but your alveolus is like a water bottle. It just really won't expand at all. And then we have some other scenarios as well. We have our equation. So I kind of talked briefly about why we have these negative pressures. However, our change in pressure is going to be a positive value because you can do the math, but you'd have to do absolute values between the equation there on the denominator. So our change in pressure is just going to be our end result minus our beginning result. Take the absolute value of that because it's going to be our change in pressure, and then you can actually calculate the compliance. It can be measured. Compliance can be measured. It's really out of the scope of this video. You're going to have to breathe into a nice closed system, so a spirometer. It's going to measure different pressures at different volumes. You're going to have to have a esophageal probe as well in some of those scenarios. And then lastly, we have our surfactant, which helps break up some of that water pressure, so that way all of our lungs aren't completely collapsed at the very end of exhalation. Because if we didn't have any surfactant, this water force would really drive our alveolus to collapse. I keep making that mistake. So we have these nice little collapsed alveolus. Well, when it's so collapsed, it takes a very large force to break up these collapsed alveoluses. So in this example, let's say all of our alveoluses were collapsed because we just don't make any surfactant. We'd have our change in pressure. We'd have our volume. So this is our volume, pressure volume curve. And remember, we talked about it earlier. We're working so much pressure. And then finally, once we open up the alveoluses, then we get our little change in volume. And here's our hysteresis, which we talked about. Yeah, I think this is a pretty good lecture. If you have any questions, comments, or want to know a little bit more about these pressure volume curves or lung physiology or lung compliance, be sure to let me know. Either email me, send me a message, leave a comment, whatever it is, I'll try and get back to you as soon as I can. Thank you for watching. Have a good day.